So we just got done with 6.7 where we used Riemann sums, or in other words, we drew rectangles to approximate the area under the curve so we could approximate definite integrals. Some of you may have thought or noticed, like rectangles aren't always the most accurate. You know, if I go a rectangle from there up to there, like it's not going to be the most accurate graph we've done. So this may have occurred to some of you, maybe it didn't. But there are other ways we can measure the area under the curve, and one that's really effective is doing a trapezoid. So for example, if I wanted to go from 4 to 5, right, I could do a trapezoid. It'll look something like that, and that'd be a lot better approximation than if I did a rectangle that fit under the curve. So that's what we're doing in 6.8, is instead of using Riemann sums, when you hear Riemann sums, you should think rectangles. That's what it's talking about. Instead of using Riemann sums or rectangles, we're going to use trapezoids to approximate the area. Just to remind you of the formula for the area of a trapezoid, it's 1/2 the height times base 1 plus base 2. What you're really doing, right, is you're adding base 1, you're finding the average of base 1 and base 2, right? So if I got base 1 and base 2 right here, if I add those together and then times by 1/2, I'm taking the average of the two bases, and then I'm timesing it by the height. We're used to seeing trapezoids this way, right? The two bases have to be parallel to each other. You see that side is parallel to that side. Those two sides are parallel. Okay, and this would be considered the height. Now, if you go back and think about this trapezoid we just drew back here to approximate it, this trapezoid is like flipped around. So now my one base is on that side, the other base is on this side, and then the height would actually be this distance right there. So if I flip it around like this, instead of calling it the height, we're going to refer to it as the width, because you're thinking on the x-axis how wide it is. And then we'll refer to the, instead of base 1, we'll call it height 1. And instead of base 2, we'll call it height 2. Okay, so since trapezoids are used to approximate the areas, they're usually vertical, we're going to write the formula this way. It's the same formula, okay, right? We're just changing the height to the width on the x-axis. And then the base 1 and base 2 are changing the height 1 and height 2 because we're measuring vertically with the bases. To approximate the value of a definite integral using trapezoids, we do the same strategy as Riemann sums. We just take all the areas and add them together. The only difference is that they're trapezoids instead of rectangles. So here's one right here. It says approximate the area under the curve from 0 to 10 f of x d of x by adding the area of the 5 trapezoids shown in the graph. Okay. One thing, just be careful with this. This is actually a triangle, right? You can use the area of a triangle there if you want to. The area of a trapezoid always works. So I'd go like this. I'm going to do it with the trapezoid. So that first trapezoid, number 1, I'm going to go 1/2 times the width. The width is this distance right here, from there to there. Okay, so from 0 to 2, which is 2, times by, and then I got height 1 and height 2. So my first height is right here. That's my first y coordinate right there. It's 0. Plus height 2, which is this one up here, it's 4. So that's the area of that first one. Now, if you just want to do the area of a triangle there, that'd be fine, right? It's 1/2 the base times the height. It'd be 1/2 times 2 times 4, which is the same thing as we're going to get right there. Plus, okay, let's do that area 2. It's 1/2. The width of that one is going from, I think that's 2 to 5. So the width is 3 times height 1. Height 1 is this height right here, which is 4. Height 2 is right there, which is like 3. Okay, plus, let's do the third one. That width is 1. The first height, see, the first height is 3. The second height is 2. So I've got 3 plus 2 plus, let's do the fourth one. So notice on the fourth one, it's actually just a rectangle. The trapezoid rule still works there, so you can use a trapezoid formula, but we could also just do the rectangle. It's just 2 by 2. But if you do, let's just show how the trapezoid gives you the same thing. If I do the trapezoid rule, I go 1/2 times the width, which is 2, times height 1, which is 2, plus height 2, which is 2. So 1/2 times 2 is 1, 2 plus 2 is 4. You times that all out, you get the same thing as the area of that rectangle. Okay, and then we got 5 over there. 1/2 times, so you always have to have the 1/2, that's just part of the formula, times the width, which is 2, times height 1, which is 2, and the second height is 5. So this would be a 2 plus 5. Okay, work those all out, add it all up, and you got your answer. So they have this note in your book, which is kind of what we were just talking about. Nothing new, but it just says that, right? It says the area for the formula trapezoid also works for a triangle. That just means either one of your heights is going to be 0, just like it was here, right? The height was 0 right there. The other option is, just to be aware, is you could totally take this shape and draw a line right here and just make a bunch of rectangles and triangles. And that works, right? You can always divide a trapezoid into rectangles and triangles. So if you forget the formula, you can always do that. Here's kind of a cool thing. I'll let you guys think about why this works. This last part says you could use the average values of a left and right Riemann sum. So with rectangles, if you took the left Riemann sum and you took the average of it with the right Riemann sum, you'd actually get the exact same thing as you would get using the trapezoid rule. So that's kind of cool. I'll let you kind of think about and figure out why that is the way it is. Okay, let's do another example. This one says use these trapezoids with 4 equal subdivisions to approximate the area shown. This one has equal subdivisions. So we could do this one of 2 ways. You could do it individually as individual trapezoid, or there's actually a kind of a shortcut way we could do it. So we'll do it the first way, just the way we've done it individually. Then I'll show you the shortcut if you wanted to use it. Okay, so let's start out. That first one, we're going to go 1/2 times by the width, which is 10, going from 10 to 20, times by height 1. It's right up here. Height 1 is 1.8. That's that point right there. And height 2 is 2. That's that point right there. So 1/2 times 10 times 1.8 plus 2. Okay, plus 1/2 times 10 times by, now this height would be the 2, and this height would be the 2.5. Plus, next one, 1/2 times 10 times by height 1, which is going to be the 2.5, plus height 2 on that one, which would be the 3.5. Okay, plus, we're on our last one now. 1/2 times 10 times height 1, which is 3.5, plus height 2, which is 2.2. Okay, calculate all that, you got your answer. Now, if there do have equal subdivisions, there is another option. Notice how the 1/2 times 10, you have it on each one of those, right? 1/2 times 10, 1/2 times 10, 1/2 times 10. If you wanted to, if they have equal subdivisions, you can go like this: 1/2 times 10 times by, and notice how the first height, this height right here, is only included once because it's only on the one side of the trapezoid. So I just take the first one, 1.8 plus. But after that, right, I've got a 2 there and a 2 there. So I have to times all the inside heights by 2. So 2 times 2. Then I've got a 2.5 and a 2.5. So I got to times it by 2. Plus, then I've got a 3.5 and a 3.5. I got to times it by 2. Plus, and then the last height, 2.2, is only included once. So that's a shortcut way of doing this rule. Makes it a little bit easier. But this only works if it's 4 equal subintervals. So you see the 1/2 and the 10. Notice the important thing here is that the first height you do not times by 2, and the last height you do not times by 2, but the middle ones you all times by 2. Now that isn't a shortcut you need. I mean, that's not necessary, but it does save some time if you have equal subdivisions. You know, it's a little bit shorter than doing that top one up there. Either one is fine though. Okay, we're going to kind of switch gears here a little bit. We're going to come back to this idea of Riemann sums and trapezoids and finding area. But before we do that, I want to review with you really quick summation notation. You guys did this last year in Math 3. You want to make sure you remember it. So if you look at this first problem, it has, we have the summation of from k equals 1 to 7 of the square root of k. So let me just remind you what that means, and I'll move this old one down here, then we'll try that one next. Okay, summation means you're adding. So what we're doing is we are taking, we're plugging one in first. I plug one in and I plug it in. This is what I'm plugging it into right there. So if I plug one in, I'd get the square root of 1 plus, and then I keep going. I have to plug in 2, 3, all the way until I get to that top number up here, until I get to the 7. So I plug in 2 second, 3 next. I just keep going all the way up until I get to the top number, which is 7. The upper, this sometimes we call it the upper bound. Okay, so if I add all that up together, that's what this equals. So that big, it's a Greek letter, right? It stands for, in math, it means summation. Okay, this is the equation I'm plugging it into. I start with 1, plug 1 in first, and I go all the way till I get to 7. You guys take just a second, find out what this one's equal to, this bottom one. So pause the video if you want, work it out, and then come back. By the way, these examples aren't in the book. I just want to review with you a little bit of summation notation. So on this one, you plug 1 in first. If I plug 1 in, I get 2 times 1 is 2, plus 1 is 3. Plug in 2. 2 times 2 is 4, plus 1 is 5. Plug in 3. 2 times 3 is 6, plus 1 is 7. Plug in 4, get 9. Plug in 5, get 11. Plug in 6, you get 13. Plug in 7, you get 15. Plug in 8, and you get 17. Add it all up together, and that's your answer. So hopefully that's a good review of what summation notation is. That's going to be important here in just a second. Hey, real quick, let's actually write these two using summation notation. So I want to go from 1 to, I want to add up 1, 3, 5, all the way up to 13. So I'm going to go like this, draw my symbol here. We're going to start with k equals 1. Got to come up with our equation. So let's come up with the equation that represents this. Think of the y equals mx plus b. It's going up by 2 each time. So I think my equation is going to be 2x. Now, what we usually have to do, this is the first term. Usually we want to go back 1 to the 0 term. So if I go back 1 more, it'd be at -1. So just try it really quick. If I plug, and to make sure it works, plug 1 in. 2 times 1 is 2, 2 minus 1 is 1. Plug in 2, 2 times 2 is 4, 4 minus 1 is 3. Plug in 3, the third term right here. 2 times 3 is 6, 6 minus 1 is 5. So that's my equation right there. And then I got to figure out how far I have to go to. So 13 is what term? This is the first term. That's where I'm starting, k equals 1. So if you're not sure, when does 2x minus 1 equal 13? If you solve that equation, it tells you what term it's on. So if I add the 1 over as 14 divided by 2 is 7. So I'm going, that's my formula right there. It's actually the exact same one we did here. It's just going to 7 rather than to 8. Okay. Hey, you guys try this one really quick. See if you can write, so pause the video, see if you can write a summation notation that would fit this. So we're going to start with 1 down here. You don't have to start with 1, but normally we do. Okay, I'm going to come up here. I'm taking something, I'm cubing it each time. So I think my formula is going to be a cube right here. If I plug 1 in, I get 3. I plug 2 in, I get 4. So I think it's going to be k plus 1. Let's try that. Well, that'd only give me 2. Why don't we try k plus 2? So I plug 1 in, I get 3 cubed. If I plug 2 in, 2 plus 2 is 4, I get 4 cubed. Plug 3 in, I get 5 cubed. I've got to go all the way up to 45. So I want that k plus 2. When does it equal 45? So if you try that, minus a 2 over, it'd be 43. Okay. There's writing that problem with summation notation. Okay, the whole point behind doing this is because we're going to talk about some more about Riemann sums. So I want you to look at this graph right here. So this is an example of Riemann sums, right? I have this ln of x plus 5 plus 4, and I want to take it. And right now it's divided up into, I have it divided right here, tells you how many rectangles I have. I have 25 rectangles. I'm doing a right Riemann sum. So does it make sense? If I do less rectangles, it's going to be less accurate. The more rectangles I do, So now I'm up to 45. That's going to start being pretty accurate. Let's say come pretty close to what it actually equals. If I go all the way up here, I'm not sure how far it goes. So there I'm at 146. That's going to be pretty dang close to what it actually equals. So if you look down here, this is what it actually equals. This is the definite integral. So we took the ln of x plus 5 plus 4 and integrated it from -4 to 4. It actually comes out to be, oops, I got to go down just a little bit. It actually comes out to be 43.775. So you can see with 67 rectangles how close it is. And if I keep going, there's at 128. That's even closer. See how far this thing goes. So now let me slide it over. Anyway, oh, there we go. Get to 199. It's pretty dang close to what it equals. So what we're going to talk about is you can take Riemann sums. If I add up all those rectangles, if I take the number, so let's go back to here. If I take the number of rectangles, so this is the number of rectangles up here, n. If it goes to infinity, so I take the limit as n goes to infinity. In other words, as that number of rectangles gets bigger and bigger and bigger and bigger, it's going to get more and more accurate. If I go to infinity, it's actually going to give me the exact area. So what we can do, and this is something you're really just going to memorize in the end, but what we can do is we can take a definite integral, and we can take it and write it as using summation notation. Okay, writing it this way. So right here it says, right, as the number of subdivisions increase, the accuracy of approximation improves. So if we take the limit as it goes to infinity, we call this the limit definition of the definite integral, because really it gives us a definite integral as long as you have to have that limit as n goes to infinity. So I want you to look to see how this works. Let's go back to this picture for just a second. If you look up there, this is the rectangle right here. This f of a plus k delta x, that is the height of each of the rectangles. This, the change in x, that's how wide the rectangles are. So if you times those together, it gives you the area of each rectangle. Well, the way we find that is we take the f of a plus k times this is how wide x is, right? Okay, and then we're timesing it by the width right there. And this is with right-hand heights, and that's what we're going to do is right-hand heights. What you're going to have to do is this, is you're going to have to take something that's written as a definite integral and write it using as a limit as n approaches infinity, using the limit definition of definite integral. So you're going to have to rewrite it this way, or take something that's written this way and rewrite it that way. So in the end, you're just going to have this memorized, like where does everything come from? So if you look where the a here and the b minus a come from, like those are just the limits. A is the lower limit and b is the upper limit. And then if you look in here, n is part of the formula. You'll never replace n with anything. So don't worry about n right there. So this is what it's going to end up looking like as we go through and do this. So just to make sure we understand, never plug anything for k and n. Those are just part of your formulas. The only thing you really have to plug in is a and b and a, and they all just come from the limits right here. So let me show you one of these. I think it'll make more sense once you see one. Again, this really just comes down as a definition one. So if you look at this example 3, it says, write the definite integral from 1 to 4x to the 5th dx as an infinite, write Riemann sum. Okay, so in this case, a is 1 and b is 4. And we're just going to plug everything into this formula right up here. So we're going to go like this, the limit. You have to have this on every single time. Don't forget the limit as n approaches infinity of, we do our Riemann sum. Sorry, we do our summation notation. And we're always going to go k equals 1 to n to n. Okay, and then we have f of. So if you look up here, f of x is our function. So in this case, our function is x to the 5th. So inside of there, I'm going to go inside of the x, in place of x, I'm going to plug in. So let's do this one. I'm going to plug in. I got a. A is my lower limit, which was 1 right there. That's a. So 1 plus k times. and it's b minus a. That's just 4 minus 1. So that'd be 3. 3 over n to the 5th power. All times by b minus a over n. So the b minus a would be 4 minus 1. That'd be 3 over n. Okay, and we're done. That's what it's equal to. This is exactly the same thing as this. So what I really did, this gives you the height. So as I plug 1 in, that gives you the height of your first rectangle. This gives you the width of your first rectangle. If I plug 2 in, that gives you the height of the second triangle and the width of the second triangle. If I plug 3 in, and so on and so forth, that's what's going to happen for the rest of it there. Let's do that number 4. So now we're going the opposite direction. So if you look at it, it's written as the limit definition of a definite integral. Okay, it's written that way. We want to write it just as a definite integral. So if we're going to go that direction, if you're looking up here, we need to find out what is f of x, what is my function, what is a and b. I'm going to write it as a definite integral. So I'm going to come down here. I want to find the definite integral of a to b. I need to know what my function is. So if you look at it, this, the pi halves plus k times pi over n, that is the inside of right here. So whatever that's being plugged into is my function. So it's being plugged into the sine function right there. So that is my function. So it's going to be the definite integral of the sine of x. Okay, and then the pi over n, that has to be the b minus a over n. That's where that has to come from. Well, that means b minus a has to equal pi right there. And then pi halves, if you look right there, pi halves is a. So I know what a is. So we can actually put that down here if you want to, as pi halves. All I have to really do is figure out what b is. Well, I know that pi has to equal b minus a. So that'd be b minus pi halves. B minus pi halves. So if I solve for b right there, if I add that pi halves over, I'd end up with b is equal to 3 pi halves. So that's my upper limit right here. You guys have to excuse my handwriting. That's 3 pi halves up there on top. Okay, and that's it. We've rewritten it. So all you're doing, again, this is just a memorization thing, is knowing what this formula is, right? I know if I'm going to one direction, I have to take my upper and lower limit, the b minus a, and I'm going to go a plus, and you never plug anything in for the k, you never plug anything in for the n, you just plug in for a and the b minus a, and the b minus a right there. That's it. The hard part's memorizing that, right? This would be something we want to add to flashcards or whatever, so we can give, add it to the list of many things that we need to have memorized as far as formulas go. Let's do one more here of each. These aren't in your book. I just added a couple of examples because I know they could be a little bit confusing until we get used to them. So let's do this top one right here. It says write each Riemann sum as a definite integral, and each definite integral is a Riemann sum. So this one is, using the limit definition of a definite integral. Okay, so this is written as a Riemann sum. Okay, so we're always starting out, right? Our formula is up there at the top. I'll slide this down a little bit so you can see it. Okay, there's our formula up there. This one is this right here. Okay, and we're trying to write it as a definite integral. So I know I'm going to rewrite it this way as a definite integral. I got to figure out what a and b are. A is always, so if you look at what's plugged in, you see this 2 over n. This is the inside of the function right here. I plugged in 5 plus 2k over n. That's this part right here. So we got to figure out what a is. Well, a is just that first number that you're adding right there. So in that case, it's 5. So I know my lower limit is 5. And then what did I plug this into? I plugged it into the 2 times that minus 3. So my function is going to be 2 times x minus 3. Okay, I got to find, all that's left really is to finding my upper limit. Okay, so to do that one, I know that b minus a is 2 over n. So b minus a over n is equal to 2 over n. Well, that means that b minus a has to equal 2. Well, we know what a is. A is 5. So we know that b minus 5 has to equal 2. So if I add that 5 over, I get 7. So come down here. So this is written using limit notation. This one is written using, as a definite. Why don't you guys give, let's do that top one right there. Why don't you guys give this one a try right here. So pause the video. Again, this is in your book. You'll just have to write it down. But give that one a try it there and see if you can write it as a definite integral. Okay, so I'd always start by identifying like what's the inside of the function. So the inside of this function is that part right there. Okay, so that means that whatever I'm adding in here, that 3 by itself, that's a. Okay, and then that is inside of the square root. So the square root is my function. Okay, and I just need to find the upper limit, which is 3. Well, I know that b minus a over n has to equal this part right here, which is 5 over n. Which really means that b minus a has to equal 5. Well, a is 3, so I know that b minus 3 has to equal 5. So that means that b has to equal 8. Okay, there's my definite integral right there. Here is one. Oops. Here is one that's just going the opposite direction. So this is written as, these are written as definite integrals, and we want to write them as Riemann sums. Okay, so let's try. Let's do that. This one first. So this one we actually don't know what the function is. So if we slide up there, we'll keep that formula right up there in front of you. Okay, and we'll go through and do this together. So we're going to write it down as being the limit. A lot of times you forget to put the limit as n approaches infinity in front. If you do, that's incorrect. You have to have that, right? So the limit as n approaches infinity of my Riemann sum. And we're going to go from k equals 1 to, and up here we're going to put n. Okay, so we start with f of, or in case of our function g of, and inside of g I have to plug in, has to be a, which is my lower limit, so 1 plus, never plug anything in for k times b minus a, that'd be 5 minus 1, 4 over n, times by 4 over n. And that's it. We've written it in that form. You guys try this one, pause the video, and give this one a try. This will be the last one. Let's do that bottom one. See if you can rewrite this using as a Riemann sum. Okay, so we're going to go, right, limit as n approaches infinity of, we're going to go from k equals 1 to n. Okay, and then we got to take my function 3 tangent, but in place of the x, we're going to plug in 5, a plus n k times b minus a over n. 10 minus 5 is 5 over n. Okay, and then we got to times that by 5 over n. Okay, there we go. We have it rewritten. It's a little bit tricky, but again, once you get used to it, it really is just memorizing that formula and knowing where everything goes. And you'll have some practice with that on the assignment. All right, thanks, guys. Good luck.